The notch I was trying to show you, you might still be able to see. I've already inserted the two-sector centerpiece. Okay, I'm so sorry. Thank you, Nilafar. Um, there's a notch, is what I was trying to point out. You can see this ridge running in the top part of the screen. If I get the light just right, you can see that there's a notch or a ridge inside the metal piece. And then there's a notch inside all of the other parts so that they get lined up the same direction. The windows I started out describing are these little metal guys. It's a for holding your sapphire window. There is a little plastic piece on the inside, and there's a little plastic piece that goes along the perimeter. Don't worry about this. When you're first using the machine, I will set most of it up and you will watch. The second time, I will do it about 50-50. The third time you use the machine, I'll try to sit on my hands and make you do most of the work, but I'll be watching everything you do. I'll try not to talk too much about politics and restaurants, but I probably will anyway. Hopefully I won't distract you too much, but that way you can do the work, get the experience with it, and I'll just make sure that you don't forget anything. Um, like forgetting any of the parts that go inside the window housing. Once you've got the window housing, you take this little sapphire window. It's sapphire because it's nice and flat. What I was trying to say before is that on some of these windows, they're a little bit old and they've been scratched. So you can see the scratches if you look at them very closely, but I doubt my camera will pick it up. But what's nice is that on some of your centerpieces, there is a central plastic ridge that goes down the middle. If you can align your scratch on the plastic part, you're not doing any optics through the plastic, of course. So all you have to do is make sure that you align the scratch with the center portion of your lens, of your window holder, and you don't have to worry about it affecting your optics at all. All you need is a clear window through the part that goes through your actual cell. So I've already put a window in the bottom of this guy. You can see there's a metal ridge there, so I can't put anything in from this side. I can only put things in from this side. I've already put in a window, and I put in the two-sector centerpiece. And I've got this last window that needs to go window side down in the top here, and I need to line up the keyway with this little notch that you might be able to just barely see inside the edge of the black anodized aluminum at the very top here. If I get it lined up right, I should probably stand up straight to do it. It slides right in there. And all I have to do is put in another gasket, a little round gasket that goes in the top. And this is the little lock ring that goes into holding the whole thing together. It needs to be torqued in place, but we have a torque stand, and hopefully I can get you to see that. On these rings, there's an inside and an outside. The outside is marked out. It does spin at 40,000 RPM, so it may be hard to actually read that it says out, but the outside is now facing you guys. For some reason, I like to put it on my pinky. I get a little bit of spin coat, Beckman brand spin coat, and I put a little bit onto the threads. It just takes a tiny little dot of spin coat on the threads for it to work. And it helps lubricate this thing so it doesn't bind up inside the threads of this metal housing. Because this is such a fine-tuned kind of thread, I usually turn things backwards. You turn them counterclockwise until it clicks. That means that as long as you're doing it gently, that means that you've centered the thread so that it's going to start biting in the correct direction. So if I go backwards, did you hear that click? I'll go once more around. I'm just messing it up. There's a click there. That means that now that you're oriented. It's very easy to take these sort of relatively fine threads and get them cross-threaded and strip the threads when you try to tighten it in place. Otherwise, it's pretty simple. There is a little slot that's cut into the edge of this lens bolt, this lens nut, which conveniently has a hole through the middle of it. This little notch in the lens nut matches up with this little ridged screwdriver head, this giant flathead screwdriver that fits on top of this. It fits perfectly on here, and so you can tighten this guy down, and now hopefully my sample is not going to leak out the gap between the plastic and the glass. Now, walk this way. There is a chuck. I guess you can see there is a chuck, and there is a wrench here that looks just like what goes on the chuck. This guy fits right inside this little chamber on the inside. See if that looks any better. So there is a holder for circular things. There is a lever for clamping it down. Here's my circular sample cell. I need it to be torqued in place so that it's as tight as possible. I hold this guy down, I pull the lever, and it locks my sample, it locks my cell assembly in place. There's these little ridges here at the very bottom of this bolt or this nut driver. It's just like the ridges on the handheld device. But what's nice about this one is that I can have this clamped in place, and I can take the good old-fashioned torque wrench, which has a nut driver on the end of it. The nut driver goes into the top, and I can read on this dial what torque I'm setting. I usually want to torque these things to about 120 pound-inches, which is the yellow scale here. When you're doing this again, when you're doing this in person, I'll be there to help you. Every now and then, the sample will rotate. There we go. So it's torqued in place. To let my sample out, you want to put a hand over the top of this thing because there's a spring that will push my sample up out of here. When I release the pressure on this handle, my sample pops out. There's my guy. I can take it out. You can see, if you look closely, that some of the threads are visible at the very top because I've pushed this ring down a little. So what I can do, I can take my super high quality, high purity water, which is just sitting out in an open beaker. I can take my fairly cleaned up syringe, and I can load it up with my 420 microliters of sample. Ideally, you want to do this as carefully as possible so that you know exactly the same volume. When you're loading your sedimentation velocity experiments, you want to make sure you load them exactly the same volume. If you are one of the rich labs that has lots of really fancy gel loading tips, you will find certain types of gel loading tips that are very, very narrow for a long ways. Those are the ones you want to steal and hoard and keep for yourself so that you can do your sedimentation velocity experiments. The tip should be about as narrow as the needle, the plastic needle on this. The reason we use plastic instead of metal is because these centerpieces are made out of plastic. They're made out of Epon, which is just a name brand for a certain type of plastic. And they can be scratched, and they have to be kept polished smooth, because if there's scratches along it, then your protein is going to mix instead of sediment. So we have to keep the plastic as clean as possible, basically. And that means using plastic parts that go into the bits that touch your equipment. So usually I load in the buffer first. If you look in the top, there's these little holes in the sample holder. One side's got the bottom, one side's got the nut that we just put in, and there's these two holes here. If you look in the instructions, and I have a copy of them up top here so I never screw it up, this end, there's two holes to load. One has the reference and one has one has reference or buffer, and the other has your protein. You don't want to screw them up, because if you look closely at the shape of this guy, there's actually two sectors inside that two-sector cell. They're not straight rectangles. They're like pie shapes. And it's very important you put the right one in the right side. So I have a little diagram here so that when I have the cell oriented towards me, the buffer goes on this side. I tend to be right-handed, and I like to load things. I only like to load the right-hand side window. So now, from my view, the right-hand side window is this one. The right-hand side window is on this side. So I will load in by just inserting the plastic needle to the top of the syringe. I don't know if you can see any of that. I will go slowly to make sure that I don't end up with any air bubbles or weird things happening. And I will try to load this bad boy up to 420 microliters exactly in my sample. It might be hard to see that there's a little meniscus there, but you can if you look really closely on this side. Turn it around because I'm right-handed, and I'll do the same thing with the sample on the other side. Today's sample, for giggles, is a mixture of 3 proteins and DNA. It's going to be a miserable sample to run in the XLI because 2 of the proteins have heme groups and are different sizes. One of the protein is about the same size as the protein that only absorbs at 280, and DNA is going to destroy all of our ability to do spectroscopy. I'm going to try anyway. The reason I'm doing it, though, is that in the new instrument, in the Optima instrument, I'll be able to measure independently the 3 wavelengths of things. The DNA is large. It should clear the sample area quickly, but I can track it at 260 nanometers. And even though it absorbs a lot, at 280 nanometers, it's probably going to cause havoc for the rest of my protein, but it might leave quickly. The other 2 proteins are hemoglobin and cytochrome C. They have heme groups. They absorb at 400 nanometers. So I can do a 3 wavelength experiment. This is sort of complicated, but I'll do a 3 wavelength experiment in the new machine looking at 260, 280, and 400 nanometers. 280 nanometers, I should be able to see 2 proteins. Well, I should be able to see all 4 things. At 260 nanometers, I'll only be able to see the DNA. And at 400 nanometers, I'll only be able to see the cytochrome C and the hemoglobin, but they're very different sizes, so they should separate very easily. One's like 15 kilodaltons, and the other's 60. So I'm going to load this with 420 microliters and then seal it all up and get it equilibrating, and then we can take a break, and we'll talk about setting up sedimentation velocity stuff tomorrow. Does anyone have any questions? Can everyone still hear me?
Yes, we can.
Yeah.
What could go wrong? Loading protein always makes me nervous. I don't know if you can see what's going on, but I'll try. One of the reasons loading protein makes me nervous is that the hole that we're going through is really narrow, and if it ever gets wet, you're trying to displace gas through this narrow opening between the hole and this plastic syringe, this plastic needle, which is all bent now. If that ever gets clogged with anything, you try to put your precious protein in here and it just starts bubbling out the top. And it's super annoying, especially when you're the one who has to purify the protein. So I put my protein in. You can see one chamber's brown because it's got heme and cytochrome C in it and BSA and DNA, but you can't see that. I don't know if you can see the difference between the two. The openings are still there. It's not going to leak out through these little holes, but I'm going to have to cut some gaskets real quick and bolt it in place. It's very easy to do. I usually put 2 gaskets in every hole to make sure that I don't end up losing material. I do not like it when my sample leaks out into my chamber. The AUC should not be seeing a lot of liquids, and especially when those liquids are proteins I've had to purify. So I cut myself a bunch of gaskets. Where's my sample? Ta-da. I have a bunch of fancy tools. For those of you who like to get your own equipment, this is a good excuse to get your PIs to purchase some nice stuff. These are probably one of my favorite pairs of tweezers because they're very soft. They're rounded and they're pretty good at grabbing these plastic parts that go inside this little hole. It's hard to show you, and you'll see when you get here in person, but here's an empty one, but there's these 2 little holes, and the holes are also threaded. You put in a gasket, and to seal the whole gasket up, you have this tiny little screw-headed thing. It's a stop plug that stops the stuff from leaking out. It works okay, but getting it aligned with a piece of plastic that's in its way is a little bit of a problem. Again, it's nice to have like a dedicated screwdriver that no one steals on you. That fits just perfectly the size of these guys. I usually go backwards to make sure it threads in right so I don't end up stripping out the threading on these metal housings where everything's held in place. When you're loading your first sample, I will probably tighten it for you the first couple times so you get a sense of feeling how tight it has to be. It has to be tight enough that you don't leak liquid, but if you make it too tight, it'll start deforming the plastic and it won't fit in the rotor correctly. So that's most of loading a sample. Questions or anything? Now, it's a centrifuge, and I'm going to be spinning at 40,000 RPM. So the weight of this thing has to be exactly the weight of what's on the opposite side of my rotor. I have a balance right here. I don't know, 0.0 grams. Everything is up. I'll probably let them equilibrate all night. Spin on this stuff. Is it leaking already? No, it's all right. I'll do a quick spin on this stuff in the evening, and we'll grab the data tomorrow and take a look at it. I suspect it's going to be a lot more interesting when we use the new machine on this because I've given it a very difficult challenge to try with this particular setup. Are there any questions? it's cooling at 6.5 degrees. I don't know what my computer's doing, but it seems to be messing up a lot. Hopefully you can still hear me. The vacuum is at 0. I'm going to turn the vacuum off so I can open the door. Otherwise, a lot of this is just like a regular centrifuge. Setting up the run I can show real quickly too. Once this opens up, I'll show you how to take the rotor out and the spectrometer out of the chamber, and we'll see how well this stuff behaves and looks. It takes a few minutes for all of the gas to re-equilibrate. That's probably hard to see. Taking this thing out of the chamber usually requires 2 hands. This here is the $50,000 part. There is a laser interferometer here. I'm sorry, I have that backwards. The laser interferometer is here. The monochrometer is there. Normally it goes into its special chamber to be held in place. But because I'm just going to load a sample, I'm going to load one sample real quick. There's your rotor. If you look, the rotor has a bunch of laser scribed marks. I'll go over this in detail when we first use it. The rotor should always be on its rotor stand. If you look closely at the cell, there is a laser scribed mark at the bottom of it as well. So the dissectors are perfectly aligned and not rotated one way or the other. You'd line up the laser scribed mark on the bottom of your 2-sector cell with your rotor. It's easier said than done. It's easier shown than described. But basically your sample slots right inside that rotor. You can see it coming out, going back in. Because this is an important experiment, I usually double check and triple check and make sure that I have the sample as oriented perfectly as possible. You don't want to be off by a degree or 2. It needs to be aligned perfectly. Once that's aligned, you make sure you put it in the slot that is exactly opposite to the counterbalance. In the 8-cell rotor, that would be slot number 4. That will be important later. You lock your optics back in place, close the door, press vacuum, and start the vacuum up. For the computer, I mean, it's a 20-year-old instrument, so what kind of software do you expect we have? Oh yeah, glorious Windows 98. You see that? Nothing but the best. So the Beckman software has a couple of things on it. Close some of this garbage that's in the way. There's an image of how the interferometer actually looks when we start the run later. I'll make a short video of how that actually looks. The scans are controlled by this piece of the scans are controlled by this software here. I'm going to spin at 40,000 RPM. I'm going to run it at 4 degrees. I'm using the 8-hole rotor. In terms of options, I will not have a delay calibration because I don't need to calibrate. I will not turn on the radial calibration because, again, I don't need to calibrate for the radius or the delay. In terms of method is really, really simple for velocity scans. I don't want any delay in the start. I don't want to waste any time between scans. And I want you to just get a lot of scans. And at the end of the day, I'll just come in tomorrow and stop the number of scans early. I'll probably pick up 200 scans by tomorrow morning. If I were to come in and press start method scan, it would actually start scanning for me. There's a couple other things I want to set though. If you look in this different cells, there's 8 of them, 1, 2, 3, 4 different cells. There's a bunch of old comments here, but none of these are checked. None of these are turned on. So that means none of them are going to actually be measured. The cell number 4 is the one that I'm interested in. I put in a mixture of BSA, DNA, hemoglobin, and cytochrome C. It's kind of a crazy experiment. I'm going to measure at this particular wavelength. The Rmin and the Rmax stay the same. I want to measure absorbance and interference. The absorbance will be measured at 280. I'll be doing a velocity scan. If you click details, we will not try a second or third wavelength. That usually is a cause for disaster. Although maybe I should try it, but maybe some other time. I'm going to save it in this data directory. It will be 1 replicate, continuous mode, 2-channel centerpiece, and you don't have to really worry about the rest. You click OK, and once the machine has gotten to vacuum, and once the machine has equilibrated to 4 degrees, then I'll just come back and click Start Method Scan. Questions on any of that? All right. So let us break for today. I will tidy up a few things. Tomorrow we can talk about sedimentation equilibrium. I'll have another short presentation on stuff with some more data and some analysis. We'll have a quick demonstration of some sedimentation equilibrium data fitting. And that's actually a little bit trickier. Sedimentation equilibrium on paper looks better, but you really have to know that your protein is behaving well. So, and because it takes a week to do the experiment, it's usually better to do sedimentation velocity first. So we'll go through sedimentation equilibrium though, because a lot of times that's the magic thing that makes a lot of old reviewers happy. A lot of people are not used, even though the CFS analysis came out in like 2000 and people have been using it for 20 years, there's a lot of old reviewers that have never heard of it. And sometimes when we're doing this type of work, it's fighting against reviewer number 2. Questions? Hopefully that's not been too much information and not too boring. I will stop the recording when I find my mouse. I will bid you all adieu, and we'll resume again tomorrow at 10. If you have questions, I'll be online at about 9, and we can talk about installing software or setting up experiments or whatever you're interested in. All right? Thanks, guys.